3.2 measures of variation. This, according to this book, variation is the single most important topic in statistics. So this is the single most important section in this book. All right, and that's a pretty bold statement. I think this section presents 3 important measures of variation: range, standard deviation, and variance. These statistics are numbers, but our focus is not just on computing those numbers, but developing the ability to interpret and understand them. So here's the round-off rule for measures of variation. It says when rounding the value of a measure of variation, carry one more decimal than is present in the original set of data. Okay, so we've seen that little rule before. So when we're talking about this, carry one more decimal. Range of a set of data values is the difference between the max data value and the min. So that's a very easy calculation. Range, max minus min. Important properties of range. The range uses only the maximum and minimum data values, so it is very sensitive to extreme values. The range is not resistant. So there's that word again, resistant. Okay, and when it's not resistant, it's saying that like outliers will affect the value. All right. Because the range uses only the maximum and minimum values, it does not take every value into account and therefore does not truly reflect the variation among all the data values. All right. So think about what the word variation means. Variation, how much it varies, how much the numbers vary. So then example 1, find the range. Finding the range is very simple. You find the max, you find the min, and you subtract. So quite simply, 55.6 minus 14.1 equals 41.50. Okay, remember, keep an extra decimal point. All right, here's where it gets harder. Standard deviation of a set of sample values, denoted by S, is a measure of how much data values deviate away from the mean. Okay, so for example, I'll give you a list of numbers. Okay, it's pretty easy to calculate the mean of those 4 numbers. The mean, or well, I can't say average, right? The mean is 10, right? The mean is 10, and those numbers are all equal to 10, so the standard deviation is 0. Those numbers don't deviate, those numbers don't vary from the mean because they're the same as the mean, so the standard deviation is going to be 0. Now, if I change the example and give you the numbers 0, 5, 15, and 20, you can pretty quickly calculate that mean. Add them up is 40, divide by 4 is 10. That mean is also 10. But these numbers are different because those numbers vary, right? Those numbers aren't all the exact same. I don't know what the standard deviation is. We haven't calculated. We haven't learned how to calculate that yet. But it's definitely bigger than 0 because those numbers actually vary. So we've got some symbols here. S is the sample standard deviation, and this symbol right here, that is the Greek letter. Oh shoot, I want to say that's the lowercase theta. Population standard deviation. So we'll look that up. You've got a couple of formulas here, and these formulas look crazy. All right, and I know that they look really difficult. I don't expect you to have these 2 things memorized, but you've got 2 different formulas for sample standard deviation, or the standard deviation of a sample. So, you know, look at all this stuff going on here. We've got a big square root. We've got a sigma, meaning sum. We've got a mean right here. Okay, a lot of stuff going on. And then the second formula is kind of ironic. I think that it calls it a shortcut because it looks like it's more complicated, but it is actually a little bit quicker if you're doing it by hand to use the bigger equation. for standard deviation. Important properties of standard deviation. The standard deviation is a measure of how much data values deviate away from the mean. So again, remember that example when I gave you all these tens, those numbers don't deviate at all from the mean, and that standard deviation was 0. We're going to have a lot more interesting examples than that, but that kind of gives you an idea of what we're talking about. How much do the numbers deviate away from the mean? The value of the standard deviation S is never negative. It is 0 only when all of the data values are exactly the same. Larger values of S indicate greater amounts of variation. The standard deviation S can increase dramatically with one or more outliers. The units of standard deviation S, such as minutes, feet, and pounds, are the same as the units of the original data values. The sample standard deviation S is a biased estimator of the population standard deviation, which means that the values of the sample standard deviation S do not center around the value of the population standard deviation. Okay, so we'll talk a little bit more about that later. I think that's kind of a tough definition. You might want to read that again. Okay. Now, example 2, we're going to calculate a standard deviation and make sure you write small. Okay, write small, and also shoot, hold on a second. I probably should have included this slide in your notes. This slide contains the actual steps for calculating the standard deviation. I think it's probably overcomplicating the issue, but you could find this slide on page 100 of the book. You could take a picture of it now or later, or you could go, find the book, find page 100. These are the actual steps. But what happens, what we're doing actually, is we're taking this equation and just kind of walking through the equation. So the equation for finding that standard deviation was big square root of sigma x minus the mean squared over little n minus 1. Okay? So remember, x was just the data values. N minus 1, or n, is going to be the number of numbers, I guess, right? Little n is the number of numbers in that sample. So basically, if you thought about that equation and just think about the order of operations in this problem, that's the steps. Okay, if I was going to calculate this formula, the first thing I would have to do, according to order of operations, is go inside those parentheses and calculate the mean. All right, so that's step 1. Step 1 is find the mean. Okay. So the mean is just add up the numbers and divide by the number of numbers, right? So we're going to add 38.5 plus 55, right small, 0.6 plus 22.4 plus 14.1 plus 23.1, and we're going to divide by 5. I believe we did this same example in the last lesson. 153.7 over 5 is 30.74. Now that is not the standard deviation. We're not even close to the standard deviation. That is just the mean of those 5 numbers. Okay? Go back to the equation and think about the order of operations. The next thing you'd have to do is take your x numbers minus that mean. We're inside the parentheses. And so step 2 is going to be x minus the mean. Okay? So you have to think about what x is. You have to know what x is. X is just each one of your individual data values. So it's saying we're going to subtract each of those data values minus the mean. So 38.5 minus 30.74 and 55.6 minus 30.74, 22.4 minus 30.74, 14.1 minus 30.74, 23.1 minus 30.74. I'm taking each of the x values, each of the data values, and subtracting the mean. And I get these results: 7.76, 24.86, negative 8.34, negative 16.64, and negative 7.64. Okay? So, think back to the equation. The equation, the next step, the next thing we're going to have to do is square that difference. Okay? So we're going to square that difference, and that's step 3. So I'm going to go over here. Step 3 is x minus x bar squared. So what I mean by that is I'm going to take each of those numbers, each of those 5 numbers I got from step 2, and square them all. All right? I'll take 7.76 squared and 24.86 squared and negative 8.34 squared, negative 16.64 squared, negative 7.64 squared. And so once I square those numbers, I get 60.2176 and 618.0196, 69.5556, 276.8896, and 58.3696. Now, you've never seen one of these problems before, or never seen these steps before, but you might be able to tell me what the next step is, because if you look at the equation, it's the next thing that would happen in that order of operations. Okay? Anybody know what I'm going to have to do next? Next thing was going to be the sigma. And sigma means what? Sum. We're going to add those numbers up. Okay? So I'm going to put step 4 right here. Step 4 is sigma x minus x bar squared. So all I'm going to do, let's change colors here. All I'm going to do is add those 5 numbers together. Okay? Add those 5 numbers together, 60 point plus 618 point plus 69 point. Add those things together, and that's 1083.0520. Okay? So think about the equation, and the next step is the next step in the order of operations for that equation. You're going to have to divide by n minus 1. Okay, well, little n is the number of numbers. That's 5. So n minus 1 is 4. Okay. Step 5, we've got the sigma of x minus x bar squared. And now we're going to divide by n minus 1, or that's 1083.0520 divided by 4. And that's 270.7630. Okay. So I just divided by n minus 1. What do you suppose the last step is going to be? The last thing, I got to take the square root of all of that junk. Okay, so step 6 is going to be the square root of everything that I've just done. So the square root of 270.7630 is 16.45. What are the units? Megabits per second. That's a long problem, okay? And I know that you haven't seen those steps before, okay? Those steps, to me, seem overcomplicated because all we're doing is just running through the equation. We're just running through the operations in that equation, but that is the standard deviation. That is a number that tries to quantify how far those numbers are from the mean. How much do those numbers vary from the mean? Okay. Number 3. Okay, so this says let's do the shortcut formula. The shortcut formula, and so remember the shortcut formula. I know you don't have it memorized, but that was the square root of n times sigma x squared minus sigma x squared all over n times n minus 1. Okay. So it's kind of the same deal. You're just trying to recreate this formula. So step one, I'm going to do sigma x. And I suppose you don't have to do it this way, but sigma x just means add up the x numbers. 38.5 plus 55.6 plus 22.4 plus 14.1 plus 23.1, 153.7. Okay, we're not calculating the mean. We're just doing the sum of those 5 numbers. Okay, so next thing I'm going to do is let's just take that and square it. Okay, so step 2, I'm going to do sigma x squared. So we just do 153.7 squared. Uh-oh. No. I'm sorry. I jumped the gun a little bit. That is going to be in my formula, but we're going to save that for later. That's an easy calculation. I just messed that up. All right. Sorry about that. Sorry about that. We will get there, but we won't. I don't want to do that next. Okay. I actually want to do this part. It's confusing because both of them say sigma x squared, but one of them's inside parentheses and one of them's outside parentheses. So I'm doing the sigma x squared. And so if you think about what that means, that's the sum of the squares of the x numbers. And so in that case, I'm doing 38.5 squared plus 55.6 squared plus 22.4 squared plus 14.1 squared plus 23.1 squared. So you add all that up, and that's 5,807.79. Okay, I'm just trying to build out the formula there. So we know from before, this isn't really a step, but we know from before that n equals 5. So if you know those 3 numbers right there, then you've got enough to just plug it into your equation. Okay, all we have to do at this point is plug in. And so step 4, I'm just going to go ahead and build out the equation. I've got a big square root, and n is 5. And then my sigma x squared value was 5807.79. And then I'm going to subtract sigma x was 153.7, but here's where I'm going to square it. Okay, so I could have done it earlier when I started to, but there's no point. We can just do it in this step and plug it in. Okay, close that parenthesis, sorry. And on the bottom, n was 5, so you're going to have 5 times 5 minus 1 right there. And so if you've got calculator skills, you should be able to type that in. It's going to end up simplifying a little bit. The top is 5415.26. And then on the bottom, we've got 5 times 4 is 20. If you divide 5415.26 by 20, you get the square root of 270.763, and that number might look familiar from before. We take the square root, and we're going to get 16.45 megabits per second. So that was a little bit faster maybe than the other way. Either way, example 2 or example 3, it's kind of a pain to have to do that by hand. All right, we've got a lot of technology that will do some of this stuff for us, but there you go. We've got 2 different methods for finding that standard deviation of that sample of numbers. Range rule of thumb for understanding standard deviation. Range rule of thumb is a crude but simple tool for understanding and interpreting standard deviation. The vast majority, such as 95% of sample values lie within 2 standard deviations of the mean. Okay, I think some of this symbology gets kind of tricky, but remember this is talking about standard deviation. And this from last lesson was the mean of the population. Okay, that was mean, and then 2 standard deviations. So it says significantly low are numbers that you take the mean and then subtract 2 times the standard deviation. Significantly high are values that are the mean plus 2 standard deviations, and values not significant are in between. So I know it's kind of tough for students to really nail down new symbols and stuff, but here's the mean. Think about it like a number line. And if you go 1 standard deviation and then 2 standard deviations, you've got a bigger number right here. Okay, so they're calling anything above that significantly high. And then if you subtract a standard deviation or 2, once you get to 2, anything to the left of that on a number line would be considered significantly low. Anything in between, they're calling not significant. So the range rule of thumb for estimating a value of the standard deviation, we just found the standard deviation up above was 16.45. That was our answer, 16.45, and we did it 2 different ways. But they're saying to roughly estimate the standard deviation, you can use this formula, okay? And this is not equal. This is just some kind of rough estimate. So if you look back at that example 2 and 3, the max number, think about the range. The range we found was 55.6 minus 14.1 was 41.5. That was the range. And so this formula is saying you can make a crude estimate by dividing the range by 4. You divide the range by 4 and you get 10.38. That's not the answer. The answer was 16.45. This is just a crude, rough estimate. To complicate the matter, now we've got a new formula for standard deviation of a population. Remember, we've got a sample and we've got a population. Population is all of the values. Sample is just some of the values. Okay, so it's a different formula used to calculate the standard deviation of a population. instead of dividing by n minus 1 for a sample, we divide by the population size, capital N. So it's tricky because you've got two different n's and you have to remember which one's which. Little n is the number of numbers in the sample. So in our example, there were 5 numbers in that sample. Okay, but big N is the number of all of the items, whatever we're talking about in that population. Okay, so the formula looks very similar though, right? Okay, we got the square root of sigma of the x numbers minus the mean squared. All that's the same. The only difference is we're dividing by this n instead of what was it before, in little n minus 1. Okay, so it's just a little bit different. I'm not going to expect you guys to have all these formulas memorized and stuff, but you do have to know what the letters mean in order to make sense of everything that you're talking about. Okay. The variance of a set of values is a measure of variation equal to the square of the standard deviation. Okay, I like to remember it a little bit differently than that. Okay, I think about standard deviation equals the square root of the variance, and that's pretty much the same thing as what they said. And that, like, as far as memorizing stuff, that's something that's pretty easy to memorize, I think. Standard deviation is the square root of the variance. And that's what this says, just kind of backwards. It says the variance is the standard deviation, or is the square of the standard deviation. Okay, yeah. So sample variance is s squared. That's the square of the standard deviation s. Population variance is this, I think it's a sigma. I think I called it theta earlier. That's a sigma. Okay, sigma squared, which is the square of population standard deviation. All right, sigma. So again, you've got all these symbols, and it's really hard to keep them straight, okay, because they all kind of mean the same thing. That's sample standard deviation, that's population standard deviation. That's sample variance, that's population variance, okay? But one thing that is consistent, standard deviation, whether it's S or sigma, is the square root of the variance. Important properties of variance. The units of the variance are the squares of the units of the original data values. So instead of inches, it'd be inches squared. Feet squared. And that should make sense because you're going to end up taking the square root of that. Square root of inches squared gets us back to inches. The value of the variance can increase dramatically with the inclusion of outliers. Okay, here's this term again, not resistant. Not resistant means that outliers mess up the numbers. The value of the variance is never negative. It is 0 only when all of the data values are the same number. The sample variance, S squared, is an unbiased estimator of the population variance. Right, there's that term again. I think it's we're going to talk about that a little bit later. I think that's kind of a tough definition. Why divide by n minus 1? Read this carefully. There are only n minus 1 values that can be assigned. I should say B right there. Without constraint. With a given mean, we can use any numbers for the first n minus 1 values, but the last value will then automatically be determined. So I guess they're saying if you already know what the mean is, you know, and you've got like all but one of the numbers, that last number is predetermined. If we already know the mean, the last number is predetermined, automatically determined. With division by n minus 1, sample variances S squared tend to center around the value of the population variance, sigma squared. With division by n, sample variances S squared tend to underestimate the value of the population variance. Okay, I think you're going to need to read that again. I don't want to read it to you again, but you need to read that probably again. Stuff. Okay, the empirical rule is important, and it's actually one of the few things that I remember about stats class that kind of comes up. But the problem with empirical rule is even if you remember it well, it only applies when we're talking about bell-shaped distribution. Empirical rule states that for data sets having a distribution that is bell-shaped, okay, so it's got to be bell-shaped. Don't use it if it's not bell-shaped. The following properties apply. About 68% of values fall within one standard deviation of the mean, about 95% fall within two standard deviations of the mean, and about 99.7% of all values fall within three standard deviations of the mean. You may have seen this picture before, okay? You look at the number line down at the bottom, and here's the mean right there, right in the middle of your bell curve, okay? That's the mean. And so what they're saying is for this distribution, there's 34% here and 34% here. So %68 of the numbers fall within one standard deviation of the mean. And then there's another 13.5 right here and here. So if you add those together, 13.5 plus 13.5 plus 34 plus 34, from here to here is going to be about 95% of the numbers. And that's what that says. 95% of all of the values fall within two standard deviations of the mean. And then if you keep going out, here's three standard deviations. Okay, all of the numbers, well, not all of them, I guess. About 99.7 of the numbers are within three standard deviations of the mean. So you've got a few values that are going to be way out here, but 99.7 of them are within three standard deviations of the mean. Okay. Now again, that empirical rule is useful, but it only applies if it's a bell-shaped distribution. So I think you'll like doing examples because this is way easier than some of the other stuff could be. IQ scores have a bell-shaped distribution with a mean of 100 and a standard deviation of 15. What percentage of IQ scores are between 70 and 130? So this looks kind of like it's going to be hard, but think about it. Okay, draw your number line, and let's put the mean right in the middle here. All right, so we've got this bell-shaped distribution, and 100 is the mean. All right, so the standard deviation of 15, if we add 15 and if we subtract 15, we can reconstruct that picture. And what it would say is 34% of the numbers are here and 34% of the numbers are here. Okay? There are 34% of the numbers that are within 15 lower, and 34% are within 15 higher than the mean of 100. But they say they're asking about between 70 and 130. So notice if you add another 15 on there, you get to 130. And if you subtract another 15, you get to 70. So those numbers are about 13.5 here and 13.5 here. Okay, and not exactly. I've got I rounded off a little bit. It's just I think it's easier to remember without rounding to the nearest hundredth. If you round to the nearest tenth or whatever, I think it's a little bit easier to see. But if you add those three numbers up, we want to know how many of the numbers or what percent of the numbers are between 70 and 130. We'll add those numbers up, and that's, what is it, 95? The answer to this is 95% are between 70 and 130. 95% of the IQ scores are between 70 and 130. If I wanted to continue, I could continue, and I could go another standard deviation. Subtract 15, that would be 55. That is super low. Add 15, that's 145. That's super high. And what was that other number? About 2.1. About 2.1 or so. About 2.1% of the numbers are there and there. So you could add those together, and I think that gives us 99.7% are between. My computer's lagging right now. That's not good. Come on now. Super laggy. 55 and 145. That's not the answer. Ooh. 55. There we go. And 145. That's not the answer because they asked us about 70 to 130. But I like those questions. That's the empirical rule. And again, the empirical rule only works when it's bell-shaped. There's something else that's called Chebyshev's theorem. And Chebyshev's theorem does the same thing, okay? It answers the same question as empirical rule, but the difference is it's any set of data. So this does not have to be, doesn't have to be bell-shaped. So Chebyshev's a little bit harder, I think, harder to remember, a little bit harder to calculate maybe, but it's nice because it works for all the data and it doesn't have to be bell-shaped. So here's kind of the formula. The proportion of any set of data lying within k standard deviations of the mean is always at least 1 minus 1 over k squared, where k is any positive number greater than 1. All right, read that again. I know that's difficult to understand. So for k equals 2, think about k equals 2. If k equals 2, you'd have this formula that says 1 minus 1 over 2 squared. That's 1 minus 1/4, which is 3/4. Okay? So what that says is at least 3/4 of all values lie within 2, that was k, right? 2 standard deviations of the mean, 3/4. So it's not quite the same numbers as the empirical rule, right? Empirical rule, we had that 34, 68, and 95. It's not quite the same numbers. So you won't quite get the same answers, but you're not dealing with the same types of data, all right? And then if you had k equal 3, then Chebyshev's says 1 minus 1 over 3 squared. That's 1 minus 1/9 is 8/9. And so it says at least 8/9 of all values lie within 3 standard deviations of the mean. Okay, that's all that says. I suppose you could do k equal 4, k equal 5 if you want and get bigger and bigger and bigger numbers. All right, but that's Chebyshev's, and Chebyshev's is nice because it works for any set of data, not just bell-shaped. So IQ scores have a mean of 100 and a standard deviation of 15. What can we conclude from Chebyshev's theorem? Okay, so I'm not going to draw that bell-shaped distribution this time, but I am going to start off with a number line. Okay, so if I go out, if I add 15 or if I subtract 15, that's 1 standard deviation, right? Okay, 2 standard deviations, let's add another 15 or subtract another 15. So this is the mean. This is the mean plus 1 standard deviation. This is the mean plus 2 standard deviations. This is the mean minus 1 standard deviation. This is the mean minus 2 standard deviations. Okay. We can go out a third standard deviation to 145. That's the mean plus 3 standard deviations. If we subtract another 15, that's the mean minus 3 standard deviations. Okay. So Chebyshev's theorem says, okay, for k equals 2, K equals 2 was 2 standard deviations. Okay. K equals 2. 1 minus 1 over 2 squared was 1 minus 1/4 equals 3/4. All right. So Chebyshev's theorem says 3/4 of IQ scores actually it says at least that. At least 3/4 of IQ scores are between 70 and 130. So then if we look at 3 standard deviations, that's 3 standard deviations. So for k equal 3, 1 minus 1 over 3 squared was 1 minus 1/9 or 8/9. Chebyshev says at least 8/9 are between 55 and 145. So it's a similar thing to empirical rule, but different. You have a question? Yes, exactly. Okay. All right. I know we're getting close, but we're almost done. Comparing variation in different samples or populations. The coefficient of variation for a set of non-negative sample or population data expressed as a percent describes the standard deviation relative to the mean is given by the following. So we got 2 formulas here. Coefficient of variation for a sample, coefficient of variation of a population. Okay. All this is saying is standard deviation divided by the mean times 100. And it's a good way of comparing variation when means are different, like you've got very different means, or when the units are very different, okay? So let's write that down. Good for comparing variation when means are very different when units are different. Okay, real quick, round off rule. It says round the coefficient of variation to 1 decimal place. So that's weird because the other rule said keep 1 more decimal, but that's just 1 decimal place. Biased and unbiased estimators. Last thing, the sample standard deviation S is a biased estimator of the population standard deviation, which means that values of the sample standard deviation S do not tend to center around the value of the population standard deviation. I think that's really hard to read. I think you're going to need to read that again. Sample variance, S squared, is an unbiased estimator of the population variance, which means the values of S squared tend to center around the value of sigma squared instead of systematically tending to overestimate or underestimate.